Okay guys, today we are talking about continuity. But first, let's talk about continuity at a point. Let's say a function f is continuous at point x equal to c if and only if the limit of f of x as x approach to c equal to f of c. Okay, and we have the function f which is continuous on an open interval from a to b if and only if for every point in this interval, let's say this point is c, then the limit of fx as x approach to c equal f of c. Meaning if you want to show that the function f is continuous on open interval a and b, you have to select a point from a to b. Any point from a to b in this open interval and try to show that the limit of f of x at x approach to c equal to f of c. But the tough thing you have to do is to try to show that when c is in this interval, f of c must be defined. And the next thing we're going to find the continuity is that the function f is continuous on a closed interval from a to b. So to have this continuity, the first thing you have to have is f is continuous on open interval from just a to b, open interval. And there are two things that you have to do. The first one is consider at the endpoint on the left side. In this case is A, and consider the limit from the right side. So if you have the limit of f of x as x approach to a plus, it must be equal to fa. If you have this limit, that means that your function is continuous on the right side of a. And what about the end point on the left side, which is at point B? So you have to consider the limit of the function f of f at x approach to b from the left side. Once you have this function equal to f of b, this means that your function is continuous on the left side of b. Okay. Now, you may have the continuity on, let's say, half open closed interval. Okay, this is not a closed interval. I can just call half open or half closed. Actually, I'm not so sure about the name. Okay, but this is just half. I think it's half open. So let's say, so if you want to have a function f which is continuous on this interval, closed on a but open on b. It's like you have this interval that include a and all the number that is greater than a. At point b, the value in this here must exclude b. So to show that this function is continuous on this interval, the first thing you need to have is the continuity on an open interval from a to b. And consider the endpoint on the left side. So we have to consider the limit of f of x at x approach to a from the right side, and it must be equal to f of a. If you have this limit equal to f of a, you have the continuity on the right side of a, the endpoint on the left side. Now let's go to another one, which is the function f being continuous on the closed, it's not closed interval, I just call it an interval from a to b, excluding a. Okay, so what do we have right here? We're gonna have this interval that is not that does not contain a, and we have all the value that is greater than a until you reach b. For this one, you have to show that the function f is continuous on an open interval from a to b, and try to show that the limit of f of x on the endpoint on the right side, which is the limit of f of x at x approach to b on the left side, okay, equal to f of b. So you're gonna have the continuity on the left side of b. So once you have these two conditions, you're gonna have the continuity on the interval from a to close at b. Now let's show the continuity of this function. We want to determine whether or not the function f is continuous on the following interval or not. Okay. Now let's get started with this interval. So we have this function f of x equal to 1 over square root of x squared minus 4. The first thing you have to do is to try to show that this function f is continuous on this interval. So what I want to do is to let c be in this interval. Okay. What does it mean by this? That means that c is going to be less than minus 2. And try to show that when c is less than minus 2, all the value of c is defined is defined in this expression 1 over square root of x squared minus 4. So now what do we have? When x less than minus 2, how to have c squared? So you have c less than 0. If you multiply both sides by c, you're gonna have c times c greater than c minus 2, right? Okay. And then you're gonna have c squared greater than minus 2c. Okay, great. Then what do we have? Then what do we have right here? We're gonna have this c right here is less than minus 2, right? Okay. So what is minus c? So you're gonna have 2 times minus c. So u minus c is greater than 2. So you're gonna have 2 times minus c, but minus c is more than minus 2, so you're gonna have more than 2 times 2, which is 4. So that means that you're gonna have c squared greater than minus 4. Or you have c squared minus 4 greater than 0. So once you have c squared minus 4 greater than 0, you can put this whole expression into square root. So that means that square root of c squared minus 4 is greater than 0. And this square root is defined. Therefore, it's pretty obvious that thus our function f, okay, is defined at c, where c is in this interval. When it is defined as c, and we have f of c equal 1 over square root of c squared minus 4. Okay, so this is what we have. All right, and then what can we do next? So once we have f of c equal to this one, so let's find the limit. So what about the limit? We have the limit. So we need to find the limit as x approach to c of f of x. What is our fx? Is 1 over square root of x squared minus 4. So we're gonna have the limit as x approach to c 1 over square root of x squared minus 4. Then what can we do next? So we know that the limit of binomial, of polynomial always exists, right? Okay, that means that we can distribute this limit into numerator and denominator. So we're gonna have 1 over square root of limit as x approach to c of x squared minus 4. So the limit of 1 is just 1. And the limit of x squared minus 4 at x approach to c becomes 1 over square root of of c squared minus 4. That's it. Okay. So we have shown that the limit as x approach to c of f of x becomes f of c. Okay, hence what did we show? Okay, hence we have shown that function f is continuous on this interval from where? From minus infinity to 2. Okay, great. That's what we have. So we have shown that this function f, which is 1 over square root x squared minus 4, is continuous on this open interval from infinity to minus 2. Now let's go to this interval. So this interval is an interval that contains all the number that is greater than 2 but less than, oh sorry, this is 2, but less than or equal to 3. Okay, so now let's show that. So let's show that when, okay, give me a second. So we have to show that f is continuous, okay, on what? On, okay, open interval from 2 to 3. All right, and then what do we have? So we have to let C to be this open interval. Okay, then what can we do next? So we gotta have C greater than 2 and less than 3. Okay, what does it mean by this? We want to show that when C is in this interval, we have to show that this C must be defined in this function f. So what do we have right here? We gotta have this. So since C is greater than 2 and less than 3, I will multiply by C on all the side of this inequality, and C is greater than 0 already. So we gotta have 2C less than C squared less than 3C. Okay, and C is less than 3, we gotta have C times 3 times 3, which is 9, and C is more than 2, so 2C greater than 2 times 2, which is 4. So we gotta have C squared greater than 4 less than 9. So what do we have? We gotta have C squared minus 4 greater than 0. Okay, once we have this term greater than 0, we can plug this term into this square root. That means that we can have C squared minus 4 greater than 0. Okay, when it's greater than 0, you can plug it into this denominator and 1 over this square root. So that means that, what do we have here? We gotta have the function f is continuous at C, and our f of C becomes 1 over square root of C squared minus 4. And then what happened to the limit? The limit of f of x at x approach to C, our f of x is 1 over square root of x squared minus 1. So since this is x squared minus 1, which is a polynomial is defined everywhere, right? Sorry, it's defined on everywhere. Yes, it's defined everywhere. So we can distribute this limit into numerator and denominator. So we gotta have 1 over square root of the limit as x approach to C, x squared minus 1, which is 1 over square root of C squared minus 1. So that means that we have the limit of f of x at x approach to C equal f of C. And what do we have? and thus our function f is continuous at c. Okay, and where is c? C is in this interval. So therefore our function f is continuous on this open interval from 2 to 3. Okay, great. Now, but we have one more thing left to do. We have to show that our function must be continuous on this interval from 2 to 3. Okay, now what can we do next? The next thing you have to do is to consider the endpoint, right? The endpoint on the left side. Okay, so we have to consider the limit of f of x when x approaches to 3 on the left side. Now, let's take a look. Okay, so the limit at x approaches to 3 on the left side, f of x, becomes the limit of f of x, okay, when x approaches to 3 on the left side, is 1 over square root of x squared minus 4. And what does it becomes? It becomes, okay, so when x is less than 3, you can plug it into this x. So we gotta have 1 over square root of 3 squared minus 4. So we're gonna have 1 over square root of 5. Okay, and what is f of 3? F of 3 is actually just plug in 3 into x, and then it becomes square root of 5. So when the limit of f of x when x approaches to 3 from the left side approach to 1 over 5, and f of 3 is also 1 over 5. That means that this limit of f of x at x approach to 3 minus equal to f of 3. Okay, so we gotta have continuity on the on the left side, okay, of 3 already. So that means that our function f is continuous on this interval including 3. So this means that we get to have f is continuous on this interval from 2 to 3. Okay, that's it. So we have shown that this function f is continuous on this interval and this interval. Okay, and that's it for this video.